All right, guys, this is Mr. Oliver. This is going to be the solution for AP Physics 1, Unit 2 free response question number 2. This is the Unit 2 practice. So let's go ahead and get started. All right, in this question, this is kind of a longer style problem. This is something that you'd see probably for your first free response style. It's a little bit longer, multiple parts. And this is actually an old Physics B test. So it's similar in nature, but probably a little bit too mathematical, but still gives you a good idea of what to expect. And so what we have here is we've got a block of mass A being pulled by this string around this light frictionless pulley, so we can ignore the mass or anything of the pulley. And there's a constant 15 newtons pulling down on it. So first part of the question says on the dot, draw and label the components that act on the block as it pulls across the table. So the first part's pretty easy. It's just a free body diagram. So here's our dot for part A. And I'm going to try to draw this fairly neatly so we can refer to it in the future. That dot is going to have a force of gravity pulling down. It's also going to have a normal force, which should be the same approximate magnitude. In other words, the arrow length should be about the same going up. The tension in the string pulls you to the right, tension T, and then there's some friction, because it does tell you that the table has a coefficient of kinetic friction. Now, because it's kinetic, that means it's moving, and so more than likely it's probably accelerating to the right. So that means that this friction that points backwards should be less than the tension, because otherwise it would either be moving at constant speed or just sitting still. All right, so for part A, this is worth 2 points. Now on part B, the question says calculate the magnitude of the acceleration of the block. All right, so what I want to do to find acceleration is I want to take a net force equation in the x direction, because it's going to be moving to the right, and I have to set it equal to ma. Okay. Well, in this case, the net force is the difference between the tension and the friction. So our net force will be tension minus friction is equal to ma. And so to find A, I just need to divide by m, divide by the mass. And so we have tension minus friction divided by the mass, and that equals the acceleration. Well, I know what the tension is. That's going to be 15 newtons, because it's kind of stated in the problem that we're pulling that string with a 15 newton force. I don't know what the friction is, and I'll calculate that here in a minute, but I do also know what the mass is. All right, so let's take a little kind of sidestep and figure out what the friction is. So I'll do that in a different color to make sure we don't get it mixed up. All right, so the friction, if you recall, has an equation, says it's the coefficient of friction times the normal force. And it's kinetic friction. All right, well, the coefficient of friction I know, but the normal force I don't. And so you got to look at the free body diagram to see that the normal force is going to be the same magnitude as the force of gravity. They're the same. So we have the coefficient of friction, times the normal force, which is going to be the same as the force of gravity, which is just mg. And so when we go through and calculate that, 0.25 is the kinetic frictional coefficient. Our mass is 2 kilograms, and our acceleration due to gravity is 9.81. And so our frictional force is 4.905 newtons. All right, so that's going to be what I substitute in for my friction right here. Okay, so do a real quick calculation. 15 minus 4.905 divided by 2 will be our acceleration, and so we calculate that to be 5.048 meters per second squared. And so that's for part B. And guys, this is worth 3 points for this part. Okay. Now part C kind of switches it up on us a little bit, and they're going to change the scenario to where we're going to have a block of 2 kilograms on the same table, but instead of a constant 15 Newton force, we've got this second block, block B, that's 1.5 kilograms. And so now we need to ask, what's the acceleration of this block as it descends? Well, in this case, we need to take a little bit different look at it, because whenever we've added this second block, it's changed the total mass of this system. And anytime you add mass to a system of objects, it makes it harder to move. And so that makes the acceleration go down, because remember, the more massive something is, the more inertia it has, and therefore it's going to move slower under the same kind of forces. And so if I look at block B right here, block B has a force of gravity that's mass times g. Now, it's also going to be suspended by some kind of a tension, right? Tension T. Now, if I look at this, what's mass? The mass is 1.5, and g is 9.81. Well, in a lot of these older style questions, they didn't use 9.81. They just assumed that g was 10, whereas usually we use 9.81, and that's fine. But look what it is if we did happen to use 10 as our acceleration due to gravity. Well, 10 times 1.5 is 15 newtons. And so what's happened here is they've replaced this 15 Newton force with a block that would give the exact same amount of force. But the difference is the mass that's being accelerated for the whole system is going to be different, right? So when we go through and do this calculation, we have to include that new mass. So to calculate the acceleration of the block, part C, I need to know what the acceleration of the whole system is, because this block accelerating down is going to be the same acceleration as block A moving to the right. So as long as I can find the acceleration of the whole thing, I'll know what both accelerations are. So to find that, once again, I'll do F net is equal to MA. But in this case, the mass is the total mass. So I'll put a little M total there. Sorry, guys. So our net force is equal to MA, where the mass in this case is not just the block A mass, it's block A and block B mass. So we want to calculate for the acceleration, solve for the acceleration. So it's going to be net force divided by the total mass. And the net force is going to be exactly the same as what it was before. Everything else is exactly the same. So this term right here on top, that was our net force, net force, net force. Okay, tension minus friction. And so this net force is the same, 15 minus 4.905. But this time the total mass is going to be the 2 kilogram block plus the 1.5 kilogram block. We've added extra mass to the system. And so now when we calculate our acceleration, we end up getting a different value. We get 2.803-ish, somewhere around there. I think what I did is I went ahead and calculated not 15, but using 9.81. And so the number's a little bit off, but using these numbers, let's just use those numbers real quick and I'll calculate it for you. All right, so we got 15 minus 4.905 divided by 3.5. Yeah, so 2.88. 2.884. That's if we use 10 instead of 9.81. All right, don't forget to put your units. So that's our acceleration for C. For D, the question says, calculate the tension in the string connecting the two blocks. Well, this is where you can kind of go back to your equation for the whole system if you wanted to, because the tension is right here. Or you could just look at block B. Let's look at block B. Block B has the mass of B times G pulling down, tension going up, and we know it accelerates down at 2.884 meters per second squared. Okay, so if that's the case, then what I want to do is I'm going to treat downward as positive, and I'm going to write, once again, a net force equation in that downward positive y direction. So right here, we're going to say that the net force is mb times g minus the tension, and that equals ma. All right. I'm going to solve for the tension, so I'm going to take this expression, solve for T. So T is going to be equal to mB times G minus MA, where once again the mass is mass B. And so then we just substitute our numbers in. 1.5 times 9.81 minus 1.5 times 2.884. And when we calculate our tension, sure enough, it is different. It's 10.511 newtons. All right, so that's part D. Oh, by the way, guys, part C was worth 4 points on this test, and part D was worth 2. Part E is just going to be a little bit of kinematics problem. It says calculate the distance the block descends in 0.40 seconds. So it says it starts from rest, so the initial velocity is 0. We know our acceleration is 2.884 meters per second squared. That's from part C. We know the time is 0.4 seconds, and we want to find how far it moves, so I'm going to use delta y. And I'm just going to use our classic kinematic equation, delta y is equal to v naught t plus 1/2 at squared. Initial velocity is 0, so this first term cancels. And so delta y is just equal to 1/2 times a, which is 2.884, times the time, which is 0.4, and then that value squared. So our delta y for this problem, we get 0.4 squared times 2.884 times 0.5 for the 1/2. So we end up getting 0.231 meters. That's the distance that it falls. Right. Part E was worth 2 points. And then part F. Part F says if this system is set up in a laboratory and the acceleration of the 1.5 kilogram block is experimentally determined, the experimental value is found to be smaller than the actual calculated value. So what they're saying is that the experimental value of the acceleration, you can't see that, A experimental is less than the theoretical value that we calculated. So this is kind of thinking about an experiment. And the question says, if the given value for coefficient of friction is correct and air resistance is negligible, explain briefly but specifically why the experimental value is smaller. So why is this smaller than the theoretical? Well, there's a bunch of different answers for that, and any one of them would be sufficient to earn you credit. But the first thing I would look at is just look at the system here and say, well, what things are we ignoring? So one thing that we ignore is the pulley. It didn't specifically say that there is no friction on the pulley. It just says the light frictionless pulley for this one, but this new system, we don't really know that pulley is frictionless. So that's one reason. Friction in the pulley. Any added friction to the system will slow it down, and so the acceleration would be less. Uh, you could also say that the pulley has mass. And by extension, if it has mass, it has rotational inertia. And if you remember on a rotation unit, anytime you have rotational inertia, it makes it difficult to rotate it. It's just like linear inertia, regular plain old mass. But in this case, if it has rotational inertia, it's hard to get that wheel to turn. And so it's going to kind of bog your system down a little bit. So that's another reason why this experimental acceleration would be different. Okay. Another thing that could be happening is that the string has mass. And so if you have mass in the string and you're neglecting it, well, just think about it. That's a whole set of inertia, a whole number. It may be small, but it might be enough to affect the acceleration. So anything that you're ignoring, the fact that the string has mass, for instance, if you're ignoring that extra inertia, then that's a good reason why your experimental value would be different than the theoretical value. And a last one that it doesn't specifically even say is that the table may not be level. Okay, it may be tilted. Instead of being nice and flat and horizontal, maybe that table is kind of tilted up a little bit. And so whenever you have that block and it goes over that little pulley, think about it. If this thing is inclined, then this object right here would also have to fight the gravity pulling it back down the hill. And so that's another effect. And there's there's some other ones that you could think of, but in all cases, you just need to kind of tie back to, hey, because there's friction, that extra effect adds to the deceleration of the system. I mean, it makes it kind of bog down a little bit. And so that's, you just got to tie back to these reasons why you'd have a lower acceleration than what you'd expect. All right, guys, that's the end of that problem. Part F was worth the final 2 points. And if you have any questions on that one, feel free to email me. Thanks a lot. Bye-bye.